Welcome back to this course on polymer chemistry, and in this lecture we will continue our discussion on chain copolymerization, which we just started in our last lecture. In this lecture we will talk about the importance of copolymerization and then copolymer composition equation, and then go into different types of copolymerization process and resulting different microstructure of copolymer, and then talk about composition drift and monomer reactivities and then corresponding the effect of chain initiation reaction on monomer reactivities. Now, in last lecture we completed our discussion on ionic chain polymerization, and we also started our discussion on chain copolymerization, and we talked about or discussed different types of copolymerization, namely we talked about statistical copolymer, alternate copolymers and block copolymers, which could be different types of block copolymers, block, linear block graft and brush type of copolymers as well. Now, just to complete the types of copolymerization we have discussed in the last lecture, how do you write them in terms of nomenclature? If we make say copolymer with styrene and acrylonitrile, then if we do not want to specify the microstructure, whether it is a statistical copolymer, is alternate copolymer or block copolymer, then we can simply write polystyrene and write co in between, acrylonitrile. If you know that this is a statistical copolymer, then instead of co we can write stat in between, and if you know that this statistical copolymer is a random copolymer, which we discussed in the last lecture, then we can write ran in between. If you know that it is a alternate copolymer between any two monomers, say poly A and poly B, then we can write it is a ALT alternate as a alternate copolymer. And if we know it is a block copolymer, if you want to write block copolymer, then we can write poly A block poly B or poly A block poly B. In both way we can write in this case, but when you write different types of copolymers like statistical, random on alternate copolymer, you should follow this type of nomenclature we just mentioned. So, alternate copolymers between styrene and acrylonitrile, you can write, you should write poly in brackets styrene hyphen ALT hyphen acrylonitrile. Now, we were discussing about the importance of copolymerization, importance of copolymerization, why we should at all be interested in copolymers. Now, we said that when we talk about homopolymers, now we can have only limited number of homopolymers. We always using, if you have noticed, same names basically coming every time: polystyrene, polyacrylonitrile, polyvinyl acetate, polymethyl methacrylate. Like there are limited names we actually use for all the times, and commercially also if we want to, or the homopolymers which are used in large scale, they are very limited. So, basically that limits our options to choose polymer for a particular applications. Also, if sometimes happen, in most cases it happens that one single homopolymers do not possess the required or desired property we are looking for. In that case, to introduce that required property, we must mix these homopolymers with another homopolymer to get the properties, good properties of both the polymers, or we need to synthesize a new copolymer. Now, in terms of copolymers, the main advantage is that the options are unlimited. You can choose any of these monomers which were utilized to make homopolymers and then mix them, and also you can mix them in or make copolymers in different proportion. You can take styrene and MMA and get numerous amount of copolymers if you mixed them in different proportions. Say styrene is to MMA, you can get 10 is to 90, 90 is to 10, 50 is to 50. In so way you can get numerous number of copolymers, and also you can choose these different types of different sets of monomers. So, basically that tells you that the number of options in copolymer, if number of copolymers can be synthesized is unlimited. So, if you require a definite property or a property, if you are looking for a particular application, then if that property is not available in a single homopolymer, then you can, from a prior knowledge of the properties of the homopolymers, you can actually synthesize copolymer of required proportions to get that property you want. Now, you can always argue that why not just mix and blend the homopolymers, take poly A which is a homopolymer and mix poly B which is another homopolymer, and there is here also you can actually get numerous number of composition by choosing different A and B and mixing them in different ratio. But most cases you cannot mix two homopolymers. In case of polymers, two homopolymers are most cases they do not make miscible blends, and as a result the property of the mixture of polymer A and polymer B does not give you the required property we are looking for. Actually, it gives you a worse property than the individual homopolymers, unless you have a mechanism to compatibilize or miscibilize or have some sort of interaction between the two homopolymers. And to do that, actually you need copolymers of, in this case if you have a poly A and a block poly B, then you can actually use these block copolymer as a compatibilizer between poly A and poly B, and by doing this you can actually improve the property of the blend of poly A and poly B. So, what does it mean? That not only you require copolymers for improved tailor-made properties in a single polymer, but you can utilize this type of block copolymer to compatibilize two homopolymer and make numerous number of blend composition. But in this chain polymers we will be discussing the chain copolymers where we are mixing monomer A and monomer B from beginning and making copolymers. We will not discuss this is not part of this chain copolymerization, where you have monomer A which you polymerize by a leaving polymerase method poly A, and then add B second monomer to make poly A and poly B. This is the most common way of making block copolymer, but we will not discuss this technique of synthesizing block copolymer in this section. We will be mainly or exclusively discussing the copolymers where you start with a mixture of two monomer and then synthesize the copolymer, and in this case as we will see that most cases making block copolymer by this method is difficult. So, and that is why the reason why you or most cases this is the process applied to make block copolymer. So, we will discuss this process in coming pages. Now, continue with the importance of copolymers. For example, if you have a polystyrene homopolymer, polystyrene homopolymer is a brittle polymer, it breaks down easily, and also it has poor solvent or chemical resistance. So, to improve this property of polystyrene, you can actually make a copolymer of polystyrene and acrylonitrile, and this actually improves the chemical resistance property of over styrene homopolymer. Now, this does not improve the brittleness or the impact properties of polystyrene too much. So, what is done industrially, you make a rubbery core. So, you make a rubbery core of polybutadiene, say by emulsion method. You make core, you take a butadiene and polymerize in by emulsion method and to make a butadiene core, and some of the double bond which has remain unreacted, you can utilize those double bonds and make these copolymers of polystyrene and acrylonitrile. These are copolymers of polystyrene and acrylonitrile, PSCO-AN. This is polystyrene coacrylonitrile. So, basically you can use this as such, or you can blend this to is another homopolymer, and because the presence of this rubbery core which are soft, this actually improves the impact property, because it is soft, when you impact it absorbs the impacts and actually makes the polymer material less brittle compared to either polystyrene or a copolymer of polystyrene and acrylonitrile. So, these are one example. This is one example where you can see that copolymerization techniques, copolymer techniques are used to improve the properties of polystyrene by copolymerization with the other copolymers. Now, if you have a three monomers, then typically we use the term terpolymer for the copolymers which are produced in this from these three monomers. Now, we will talk about copolymer composition. Now, in most cases what happened, because when you mixing say monomer M1 and M2 and you are copolymerizing from there, most cases this M1 and M2 will have difference in reactivity, and as a result what happened, one of the monomers get incorporated in the growing copolymer much faster rate compared to the other. For example, if M1 is more reactive compared to the M2, then in the propagating copolymer chain M1 will get incorporated faster rate than M2 polymer. So, as a result what will have, if you start with say 50-50 ratio of M1 and M2, you will get a copolymer at the beginning. At the beginning, you will get a copolymer which will have M1 greater than 50% and M2 less than 50%. This is in the copolymer, in the copolymer at the beginning. So, because M1 is more reactive, it will get into the chain mass faster. So, you will get a copolymer which will be rich in M1 compared to M2. So, you will have a difference in the monomers concentration in the copolymer compared to feed. Now, as reaction goes, with more and more M1 is getting incorporated in a faster rate than M2, soon the reaction medium will have less M1, because most M1 monomer than M2, because most of the M1 has got incorporated in the copolymer chain. So, free monomer concentration of M1 will be lower than the beginning. As a result, the monomer composition in the medium, in the reaction medium will be different than the beginning. So, now the copolymers which will form, say, at the later part of your polymerization, copolymerization, because the monomer composition in this case, the ratio of M1 M2 are different from the beginning numbers. The copolymers which will form, which will have different monomer content than the copolymers which formed in the beginning or at the beginning. So, what we will have? We will have a composition drift, which means the copolymers which form at the beginning, they will have different composition than the copolymers which are forming at the later part of the copolymerization reaction. So, you can understand that the monomer content in the copolymers will be different than the feed ratio at the beginning, and with time the monomer composition will be different from the beginning, and there will be composition drift. So, these things will be occurring during your copolymerization reaction. Now, to predict the monomer the composition of the copolymer, you can look at the polymerization rate of the individual homopolymers. Like, for example, if you can look at the homopolymerization rate of M1 and M2, and from that you can have idea about the homopolymerization, but the homopolymerization rate data actually has very little significance or resemblance with the rate of consumption or rate of reaction of a monomer during a copolymerization reaction, which means that if a monomer, the rate at which a monomer, say M1, undergo homopolymerization, that could be quite different when you have M2 in the reaction medium. For example, if I take, say, consider malic anhydride, we talked about that malic anhydride or say steel bean, we talked about in these molecules during our discussion on radical polymerization. Now, this monomers actually do not undergo homopolymerization by itself. We discussed about that and the reason for that, but they can undergo copolymerization in a facile way with other monomers like styrene, methyl methacrylate. So, if you have the data reaction rate data from the homopolymers, that is not useful when you predict the composition or the reaction rate when these monomers are reacting with the second comonomer to form a copolymerization. Take another example where if you consider say vinyl acetate. Now, vinyl acetate obviously undergo very fissile homopolymerization, but when you have styrene as a second monomer, what happened? Homopolymerization become very low as long as styrene is present, because the copolymerization rate of vinyl acetate with styrene is much faster than the homopolymerization. So, as long as styrene is present, vinyl acetate will only form copolymer, and after styrene is over and consumed from the reaction medium, then only it actually forms homopolymerization. So, from here also if you look at the homopolymer data of vinyl acetate and then try to utilize this data to have an idea about the copolymer composition and the reaction rate between vinyl acetate and styrene, that will be of very little significance for this copolymerization. So, basically this homopolymer data rate for these individual monomers are not very useful when we discuss our copolymerization reaction. So, we need to predict in order to predict the copolymerization composition, what you need to do, you need to construct a kinetic model, and the simplest is the terminal model. We will talk about the simplest model, which is known as terminal model. Now, what it says? It says that the reactivity of a propagating species only depend on the monomer with unit which is present at the growing chain end. The chemical reactivity of the propagating chain in a copolymerization only depends on the monomer unit present at the end of the growing chain, which means that the chemical reactivity of this propagating chain will only depend upon the reactivity of the M1 group. Now, star could be radical, cation or anion. So, this is valid, this terminal model is valid for any initiation process. To elaborate this, if we have say these two or these two, because in all these cases the terminal group or the monomer unit which is present at the growing end are same, all these will have same chemical reactivity for propagation reaction. Okay. So, this is the assumption we are making in the terminal model. So, what are the 4 possible propagation reaction possible in during this copolymerization? Let us write those. So, M1 star can react with M1 and M2 are 2 monomers produced. M1 star can react with M2 M2 2 star can react with M1 react with now these reactions in 1 and 4 where M1 is reacting with M1 and M2 is reacting with M2 from the same chain, same propagating species. These are called homopropagation or self propagation, and these two where M1 unit is reacting with M2 forming M2, these are cross propagation reaction. These two are cross propagation reaction, and 1 and 4 are homo or self propagation reaction. Now, what is the rate of reaction or rate at which M1 is getting incorporated in the copolymer chain? This step 1 and step 3 are where M1 is getting consumed and getting incorporated in the chain. So, you write K11 M1 star M1 plus K21 M2 star M1 and one two plus K22 M2 star M2. Now, how to look at these rate constants? Basically, the first number represents the radical or sorry the propagating species, whether it is radical cation or anion does not matter. So, this is first one is from the propagating reactive species and second one is for the monomer. So, 1 in the second means M1, 2 is the second means M2 and so on. Now, at any instance the rate at which M1 and M2 is getting incorporated in the copolymer chain, which will be given by the rate at which this M1 and M2 is getting consumed. So, the molar ratio of M1 and M2 in the copolymer at any instance is given by dM1, because this is the rate at which they are getting consumed during the reaction. So, you can write the rest of the things from the two expression we got in the last one. Now, we can apply the steady state where the rate of change of M1 star is 0, like we discussed in the case of our chain polymerization. At its steady state, the concentration of M1 and M2 star remains constant. So, rate of change is actually 0 at steady state. Now, the steps which M1 star is getting consumed for in the reaction 1, where one M1 star is getting consumed and one M1 star is forming. So, they are not changing the concentration on M1 star. In the fourth reaction, one M2 star is getting consumed and one M2 star is getting produced. So, they also do not change, this reaction also do not change the concentration of M2 star. So, these are the two reactions where In this case M1 is getting M1 star is getting consumed and M2 star is forming, and in this case M2 star is getting consumed and M1 star is forming. So, we can write down the expressions for M1 star and M2 star is minus K12, you can do from the expression in the last page, plus K12 and in case of M2 this is the step 2 where M2 is getting M2 star is getting produced, and in the step 3 where M2 star is getting consumed. These are basically two same reactions. So, from here we can write K12 M1 star M1. Now, we are defining two more term R1 which is K11 by K12 and R2 K22 by K21, and if we apply this condition steady state condition and use these two expression, then we can write the composition of the two monomers in the copolymer as this. Now, this expression gives the molar ratio of M1 and M2 in the copolymer formed at any instance when the monomer concentration in the reaction medium is M1 for M1 and M2 for M2 monomer. Okay. So, this is the molar ratio of monomer M1 and M2 in the copolymer at any instance where the corresponding concentration of free monomer in the reaction medium given by this M1 and this M2. Now, it is easy to express the concentrations in terms of molar ratio, where F1 is the molar ratio of free monomer in the reaction medium. So, we can write this as M1 plus M2, this is also, and if we write F1 is the molar ratio or mole fraction, this is the mole fraction of M1 in free M1 in the reaction medium, and this is the mole fraction of M1 in the copolymer. So, we can write dm1 plus dm2 1 minus f2. So, you can simply write f1 is r1 f1 plus f1 f2 or f1 by f2 is one more time, f1 is the mole fraction of the free monomer in the reaction medium, and F1 capital F or F uppercase is the mole fraction of M1 in the copolymer. Now, this expression has been verified for innumerable copolymer systems, and they are this expression is equally applicable to cationic, anionic and radical copolymerization. It is not dependent on the reaction initiation system you are following. Now, this value R1 and R2, they are almost independent of the reaction medium or reaction conditions for radical polymerization, but the values of R1 and R2 could be quite different when you talk about different initiation system, and we will talk about giving a specific example in few minutes. Now, let us talk about this monomer. In case of radical, as I said that several combination of monomer are possible, because we know that most of the monomers we have seen during our discussion, initial discussion on chain polymerization, that most of the vinyl monomers they do undergo radical polymerization. So, hence lot of monomers can be utilized or can be utilized to make copolymer by radical mechanism, whereas the ionic polymers, in case of ionic polymers the monomers are very selective. So, not every set of 2 monomers can be utilized for making ionic copolymerization. They are very selective. For example, if I take a specific example of say styrene and acrylonitrile. Now, this can be copolymerized by radical, it can be copolymerized by anionic, but it cannot be copolymerized by cationic. Okay. Whereas, if I take styrene and say vinyl ether, again it can be polymerized by radical, it cannot be polymerized because this is cannot be polymerized by anionic. In this case, it cannot be polymerized by cationic, but it can be polymerized by cationic polymerization. So, as I said that you can basically choose any 2 monomers which in most cases can copolymerize in radically, but if you want to use any of this cationic or anionic technique, then the number of pairs of co-monomers you can choose are limited, as we discussed in during our chain polymerization discussion. Now, let us discuss little more about R1 and R2. As we define R1 is given by K11 by K12 and R2 is given by K21, 22 and K21. Now, this is basically the rate at which this is R1. This is the ratio of homopropagation and cross propagation. This is a homopropagation and this is a cross propagation. In this case also this is a homopropagation and this is a cross propagation. So, basically R1 and R2, this is reactivity monomer reactivity ratios are the ratio of corresponding homopropagation and cross propagation. Now, if R1 is greater than 1, then the tendency for homopropagation is more compared to cross propagation, which means that tendency for homopolymers is more than formation of copolymerization. If R1 is 0, which means there is no tendency of homopolymerization, it can only undergo copolymerization. If R1 is 1, then both are equal, that means there is no preference over homopropagation and copolymer. So, it is a completely random copolymer is formed, and if R is less than 1, then the tendency to copolymerize is more than the tendency to homopolymerize. Now, in the expression of R1 and R2, we do not have any rate constant for the termination and initiation reactions. So, which means that if we talk about that expression, if you talk about this expression, here we do not have any rate constant coming or appearing from initiation reaction, termination reaction, and so for the from the chain transfer reactions as well, which means that the rate of initiation or termination or say inhibition or chain transfer reactions do not have any significant contribution, or do not affect the copolymer composition at all. So, basically if you talk about different radical mechanism, for example, if you talk about radical initiation by thermal initiation or a photochemical initiation or say redox reaction initiation, in all those cases, as long as your M1 and M2 are same, the composition in the copolymer would be same irrespective of the initiation mechanism you applied, and also it does not depend upon whether there is presence or absence of chain transfer reactions in the medium or not. But as I said that if the mode of initiation, like whether it is anionic, cationic or radical, that change, then obviously the composition of the two monomers in the copolymers will change. And as you can understand that the polarity of the solvent in which you are doing the reaction, and that will affect more when you have a ionic chain copolymerization compared to when you have a radical chain copolymerization. Now, let us talk about different types of copolymerization and corresponding chain microstructures, types of copolymerization and corresponding chain microstructure, Now, let us talk about the first case, where we talk about ideal copolymerization. In this case, R1 multiplied by R2 is 1, or R2 is 1 by R1, we can write K22 by K21, K12, K11. Now, this gives you the reaction with the ratio or the relative reaction of M2 star with M1, M2 and M1, and this gives M1. Now, if I consider this value as 2, let us consider this value, which means that M2 star will react twice as faster with M2 compared to M1. So does M1 star. M1 star also will react with M2 twice as fast as it reacts with M1. So, irrespective of which propagating species you have in the reaction medium, it is always the reaction with M2 will be faster and M2 will be more reactive than M1. Or other sense, M2, if you talk about reverse way, M2 will be more reactive towards both M2 star and M1 star, which means that the relative rate at which two monomers are incorporated in the copolymer chains are the same irrespective of the identity of the unit which is present at the end of propagating species. Okay. So, relative rates at which M2 and M1 is getting incorporated in the chain copolymer chain is independent of which is present at the end, and the addition of or incorporation of M2 in the copolymer chain is unbiased. That means, whether M2 will get added next to M2 star or M1 star are statistically same. So, they will the sequence distribution in this case of the repeat unit in this copolymers is random. So, you will get when you make this copolymer at the beginning, you will get more number of M2 is getting incorporated in the copolymer chain, but the M2 addition of M2 and M1 will be complete random. Okay. There will be no biasness of M1 sitting next to M2 or M1 sitting next to M1. So, which we have random distribution of or sequence of the copolymers, and also M2, if this is M2 is or F2 in this case, F2 is higher than F1 if R2 is higher than R1. Now, we can simply write R1 and R2 is 1 and use that in this expression, and we can write F1 R1 F1 and R1 F1 plus F2. Now, a special case where R1 and R2 is 1. What happen again? In this case, as we discussed earlier, that the tendency to homopropagate and tendency to cross propagate is same. So, what happened again M1 and M2 will get incorporated randomly in the copolymer chain, and F1 would be same as F1 and F2 would be same as F2, because the reactivities, the monomer reactivity ratio of these two are same and they are 1. So, obviously, the rate at which M1 and M2 getting incorporated in the copolymer chain are same as their ratio in the monomer feed. So, if I want to plot say F1 versus F1, that is the okay, 0.2, 0.4, 0.6, 0.81. This is corresponds to the 20% composition of monomer M in the free monomer in the reaction mixture, whether this is corresponds to the 80% of free monomer M1 in the reaction mixture, whether this is corresponds to 80% of the monomer M in the copolymer. Now, when R1 and R2 is R2 is 1. Okay. Now, whatever the composition in the feed, that is also in the copolymer. You have this is say 0.1, this is say 0.5, this is say 2 and this is say 10. R is 0.1, R is 0.5, 2 and 10 R1. So, in this case, because the reactivity of monomer M is lower, they gets incorporated in much lower rate than the monomer M2, where if you have the higher rate, reactivity of M1 is higher compared to reactivity of M2, then the monomer M1 get incorporated in much faster rate compared to M2. Now, these curves are similar to the vapor liquid equilibrium of ideal liquid mixture. So, that is why that is from where this name of ideal polymerization has come. Okay. Now, next we will talk about the second case. This was we discuss case number say 1A, and let us talk about case number B, where we have R1 and R2 is 0. So, you have either you can have R1 and R2 both are 0. In this case, you can R1 is, as we said, K11 by K12 and R2 is K22 by K21. Obviously, in both this is case, both the monomers M1 M2 have no tendency to homopolymerize. So, they will only form copolymer. So, M1 will only react with M2 star and M2 will only react with M1 star, only the cross propagation happen, which means you have a copolymer of this type. M1 star will only react with M2 and M2 star will only react with M1 and so on. So, you have a perfectly alternate copolymer, okay, just a alternate arrangement of the monomers, and F1 and F2 both will be 50% in this case. So, as long as there is one monomer left in the reaction will continue, and once one of the monomers get consumed, the reaction will stop there, because the second monomers, even if that is present in the reaction medium, that cannot participate in homopolymerization. So, reaction will not proceed further. So, if you plot F1 versus F2, no matter what is the concentration of F1, you always get 50% incorporation in the copolymerization. Now, this can be achieved also if one of the monomer is R1 is 0, reactivity is 0, it could be the other way around, R2 is 0, R1 is 0. If R1 or it could be R1 and R2 both are near to 0. So, in this case what happen, you do not get a perfect alternate. Say for example, if I take the case of R1 greater than 0 and R2 0, then M2 star only can react with M1 star, whereas M1 star can react with M1 star with some extent. So, what will happen? You will get a something like this, where most cases it will be alternating, but there will be some cases there will be 2 M1s or 3 M1s are sitting next to each other. So, it is essentially alternate copolymer with some random incorporation of or statistical incorporation of M1, because that is in that case there is some tendency to homopolymer M1 because R1 is higher than 0. So, that is not exclusively participate in cross propagation, this sometime can participate in the homopropagation. So, you get essentially a alternate copolymer, but some cases will with some incorporation of M1. Now, there is a third case where R1 and R2 not equal to 0 or not equals to 1. Now, you can have situations like R1 greater than 1 and R2 less than 1, or vice versa, or R1 less than 1, R2 less than 1, or R1 greater than 1, R2 greater than 1. These are the 3 possibilities. This is not happen very practically, but these 2 are very common in practice. Okay. So, what we will do in the next lecture, we will start from this case and talk about the types of copolymer it forms and the microstructure of that resulting copolymer, and also talk about composition drift in this copolymerization medium and copolymerization reactions, and also talk about the reactivity of the value of this, how does value of this R1 R2, which is essentially the monomer reactivity ratios, they how they vary with the reaction parameters and the monomer structure, how what is the effect of monomer structure in the reactivity of the monomer reactivity ratio. Okay, with this we just stop in today's lecture. So, we will come back and continue this discussion on chain copolymerization in next lecture.